Lagrange error bound is the value of the rest of the Taylor polynomial that is truncated when a polynomial of a certain degree is used to approximate the actual value of the function. This means that if the Taylor polynomial of the third degree is used in approximation, the value of the Lagrange error represents the sum of all the terms of the polynomial that are fourth degree or higher. The concept shown is alternating series error, but Lagrange uses the same principle, using the value of the truncated terms to determine how accurate the approximation is. Lagrange error bound is different from the next omitted term, but only because the value of the derivative of the next degree is replaced by m. M allows the error bound to account for more of the truncated values and increases the accuracy of the bound. Lagrange error bound is easy to use because the next omitted term does not need to be found, so you do not have to take another derivative in order to extend your Taylor polynomial. The purpose of using Lagrange error bound is to eventually define a small range of numbers that contains the actual value of the function. This problem comes directly from the 2011 AP BC Calculus test. In the test, you would be asked to find the Taylor polynomial for yourself, but since it's not directly used in our problem, I've provided it for you. This problem lends itself to Lagrange because you do not have the series written out, so you cannot find the value of the next omitted term. It is better to use Lagrange for this problem because the fifth derivative is not given to you, but the graph, and therefore the maximum value of the derivative, is. Another reason Lagrange is easy to use is that you already know the value of n because it is the subscript of r, and x is the value given to you to approximate. By looking at the Taylor polynomial, you can easily find the value of a. All of these numbers can be immediately substituted into the error bound, and the only number that you need to find is m. M is the maximum value of the derivative of degree n plus 1 from the place where the polynomial is centered, in this case 0, to the x value you are approximating, in this case 1/4. The graph shows that the derivative is definitely less than 40 on the interval 0 to 1/4. Now that you know the value of m, you can put it into the error bound, and the value of the bound can be found. I use Mathematica to make sure of my answer. The original challenge was to show that the approximation was closer than 1/3000th from the actual value. Since the value of the Lagrange error is less than 1/3000th, we know that the approximation is within the limit. Although the problem does not ask you to, the range in which the actual value of the function at x equals 1/4 can be found using the error bound. You simply subtract the error from the approximation given by the Taylor polynomial to get the lower bound, and add the error to get the upper bound. The actual value of the function, which in this problem is 1.03137, should lie within this range. We know that we did our work correctly because the actual value is within this range. Congratulations, you could pass question number 6 of the BC Calculus 2011. I hope you learned from this video because I know I learned while I was creating it.